Welcome to this video on flywheels. A flywheel is a rotating mechanical device that stores rotational energy, essential for many engine applications. We begin by examining turning moment diagrams. The torque on the crankshaft of an engine varies during one revolution and is given by this equation, where F is the net piston effort. A plot of torque versus crank angle is the turning moment diagram. For a single-cylinder double-acting steam engine, the diagram shows how the turning moment varies with the crank angle. The mean torque against which the engine works is calculated by dividing the area OGP-Kp by 2 pi. In a single-cylinder four-stroke engine, the turning moment is mostly negative during the compression stroke. It becomes positive throughout the expansion stroke. In multi-cylinder engines, the total crankshaft torque is the sum of the torques from each cylinder. Engines with more cylinders and optimally spaced cranks show a significantly reduced variation in the resultant turning moment diagram. The engine speed is maximum when the crank position corresponds to D, F, and H, and minimum when the crank position corresponds to C, E, and G based on the turning moment diagram. The fluctuation of energy in the flywheel corresponds to the work done, represented by the shaded areas in the diagram. The table shows the cumulative energy at various crank positions, starting with energy E at position C. The maximum kinetic energy of the flywheel corresponds to the greatest energy value, and the minimum kinetic energy corresponds to the least energy value. The speed is maximum and minimum, respectively, at these points. The maximum fluctuation of energy is the difference between the maximum and minimum kinetic energies. The coefficient of fluctuation of energy is the ratio of this maximum fluctuation to the work done per cycle. Similarly, we define the coefficient of fluctuation of speed. Flywheels function as energy reservoirs, increasing the moment of inertia. They control speed variations by storing energy when supply exceeds requirements and releasing it when required energy exceeds supply. Let's derive the coefficient of fluctuation of speed, denoted by K. By defining the maximum, minimum, and mean speeds and the maximum fluctuation of energy, we can derive the relationship that links these variables. Continuing the derivation, we express the maximum fluctuation of energy E in terms of I, omega squared, and K. By substituting the kinetic energy E, we find that K equals K divided by 2 times E. Here is a problem statement involving a petrol engine. The goal is to determine the coefficient of fluctuation of speed, K. We start by analyzing the energy at various crank angles based on the given energy areas. We calculate the maximum fluctuation of energy, Emax, using the maximum and minimum energy values and the provided scale factors. Then, we use the derived formula for K to calculate the coefficient of fluctuation of speed. Let's analyze another engine turning moment problem. This time, it involves a 3-cylinder single-acting engine with a triangular turning moment diagram. We need to determine the power developed and 3 different coefficients. In the design of a flywheel, the inertia from the hub and spokes is typically ignored. We consider a rim element to calculate the centrifugal force per unit length, which is critical for design. To find the total vertical force per unit length, we integrate the vertical component of the centrifugal force over half a circle. This calculation results in the formula shown. Next, we examine the circumferential or hoop stress, denoted by sigma. For equilibrium, the stress is found to be equal to RHO times R squared times omega squared, or RHO times versus squared. To calculate the diameter d, we use the relation between velocity, speed, and diameter. The mass and cross-sectional area relation helps determine the width b and the thickness t of the rim.